Welcome to Learning Intention 3, Equation of a Line. So in this video we're going to start piecing together the information that we had learnt in Learning Intention 1 and 2, so namely midpoint and distance and gradient in particular. So jumping straight into it, consider in mathematics we've got two ways of expressing mathematical models. So the first way we could do it, and what we've been looking at the last few weeks, is the algebraic representation, where we've got, say for example, x's and y's, and we try to understand the relationship between those variables. And secondly, we've got, or what we're looking at next, is the visual interpretation of mathematical models, so looking at graphs. So firstly, let's consider the graph on the right and its associated equation. So what you might notice is we've got this r squared equals x minus h all squared plus y minus k all squared. So looking at this, it's not intuitive what this particular model actually represents. However, if we go down, what we can see is the model itself represents a circle. So one of the conclusions we can quickly come to is that there are benefits in using either model. In using the graphical model, it becomes apparent quite quickly what the mathematics we're doing actually involves. So in this case, looking at this, we know we're dealing with a circle, but the downside of using the visual method is it's less intuitive to do transformations or work on. So say if I wanted to enlarge this circle, I can't actually do that, but using the mathematical model or this equation, I could enlarge the circle quite easily simply by changing the value or increasing the value of this r value here. Now again, this is above the level at what we're working at in year 10, but it just shows the power we have in representing something visually versus representing something algebraically. Going to a more classical example, we could look at the weather forecast. So if I type in the weather for Brighton into Google, it becomes quite apparent that I've got this lovely graph, and simply by looking or observing the graph, I know exactly what I can expect the weather to be like. Where in contrast, if I looked at something like on the right hand side, where we've got all the code here, if I look at this code, I'm not going to know what's going on. I'd have to think about it and read it quite closely, whereas in comparison, looking at the graph, I know exactly what's going on straight away. A more extreme example of graphs versus the algebraic model would be in, let's say, something more complicated. So this is more university sort of level mathematics, but it just shows the graphical implementation or the graphical version of a model can be quite intricate and beautiful. But again, this is well and truly above the level we're working at here, so we'll put that aside for a few more years to come. What we're going to be working on today, or in this video at least, is a simple linear relationship. So y equals mx plus b, we could say it as that. And notice with this, we've got two variables. So we've got a y here and an x value. And these x and y values, they represent the points on our Cartesian plane. So we've got the y-axis over here, and we've got our x-axis over here. And these values here, x and b, they're actually constants. So you'll remember from the Learning Intention 2, m represents the gradient. And today we're going to look at what b, or we could also call it c, represents. But pretty much having a look at our graph on the right hand side, we've got y equals x over 2 plus 3, and then there's a visual interpretation of this. So we're going to look at how to interpret an equation and graph it on a Cartesian plane. So again, going back, notice that we've got a y and an x. Now, usually we've been working with a single variable. We're definitely jumping into the realm of working with two variables. So it brings us to our point of equations of a line. Now, jumping into it, a linear equation consisting of two unknown variables can be represented in the following form: y equals mx plus c. This is called slope-intercept form. So pay attention, slope-intercept form. Now, y equals mx plus c, there are four variables going on there, and they all have an individual purpose. So as I alluded to earlier, the x and the y, they represent points on a Cartesian plane. So looking at our Cartesian plane on the right hand side, this vertical axis represents all of the y points, and this horizontal axis represents all of our x points. As we move from left to right, our x values go from negative to positive, and as we move from bottom or down to up, our y values go from negative to positive as well. So x and y represent points on a Cartesian plane. M represents the gradient, so the slope of a line. We learnt about this in Learning Intention 2. And today we're looking at a newer one, so C, the y-intercept. Going on to what the y-intercept is, consider the graph on the right. Notice where this line passes the y-axis. We actually call this the y-intercept. And what you'll notice is that the point at which it crosses the y-intercept in this particular graph is 4, and the equation that models this line has a constant of 4. So the constant, or the c, is actually the point at which the line crosses the graph. So I'll quickly jump into two example questions, and then we'll look at it in a bit more detail. So consider two equations, y equals x minus 1 and y equals negative x plus 1. To graph these two lines, I'll simply bring up my ruler and I'll set it to 45. So for every square that we go up, we're going to go across one square. And notice that this line is going to cross the y-axis at negative 1. So we'll go 0 down to negative 1. So the line itself is going to look like, let's get a green pen, make it nice and thick. It's going to look something like this. Put my arrowheads on it. And let's just annotate it. So y equals x minus 1. So recall the gradient. So the coefficient in front of the x, the gradient is going to equal, in this case, 1. And because there's a constant of negative 1, it crosses the y-axis at point negative 1. Going down to b, y equals negative x plus 1. Notice with this one there is going to be a gradient of negative 1, which can be rewritten as negative 1 over 1. So we're going to expect the line to be going downwards. So bringing up the ruler again, it's going to cross the axis at 1. I'll get a nice thick pen. And drawing the line. crosses at +1 and it's got a negative gradient of 1. Therefore, I'll annotate it as y equals negative x plus 1. So here's an example of graphing two simple lines. Now let's look at the y-intercept in more detail. So the constant c is the term without a factor of x. It dictates the point at which the graph intersects the y-axis. So notice in these examples over here, this blue line, it crosses the axis at this point here, which is 0 and y equals 7. This one crosses at 0, 0. 0 for the x, 0 for the y, and this one crosses down here. So again, x is 0 and y is going to be equal to -6 simply by looking at the numbers on the graph here. So what we can deduce from these numbers is when we have a negative constant, the graph will intersect the y-axis below the x-axis. So remember, this is the x-axis here, and this is the y-axis. So when the constant's negative, it will intersect under the x-axis. Conversely, for a positive constant, the graph will intersect the y-axis above the x-axis. So notice this blue line, it's obviously got a positive constant, so it's intersecting above the x-axis there. So, looking at a few questions, where are the coordinates of a line, or where do the particular lines intersect the y-axis? Looking at these, we know that it's always going to intersect at y equals, or x equals 0, so down there. So we can say this one is going to intersect at 0 and +3. In B, it's going to intersect again at 0 and -4. Down in C, it's going to intersect at 0, and notice they're out of order. So this term here, this is the term with an x in it, so that dictates the gradient. So we don't want that. Instead, we want the constant. So the number that doesn't have a factor of x, so this is a +3. So it's going to intersect at 0 and 3. Then over in D, we're in a slightly different form again. So let's split it up. We'll break the numerators, or we'll break the numerator up. So we'll have two terms rather than one. So we'll have -2x over 3. And then we'll use the brackets, plus 6 over 3. Going down one more, 2x over 3 plus 6 divided by 3 is 2. Then bringing the negative in, going to get -2x over 3 minus 2. So this negative, it's a -1 times 2x over 3, and then -1 times 2. So that's where the negative came from here. And finishing it off, the y-intercept is going to be at 0 and -2. Too easy. Alright, so now that we can compute where the y-intercept is, let's graph a few. So we've got a few questions here. Y equals half x minus 3. So in A, where is the y-intercept? It's going to be at -3. So let's mark -3 on the graph, right there. And the gradient is the rise over the run. So remember, m equals rise over run. Looking at this, we've got a rise of 1 and a run of 2. So for every one we go up here, we're going to go across 2. So here. Now getting my ruler, let's rotate that around just a little bit. And we want to get the ruler such that it passes through both the points. There we go. So using a thicker pen, A is going to look like that. And to complete it, I'll put the arrowheads on the line, and then I'll quickly annotate it to y equals 1 over 2x minus 3. Now the second one here, y equals 0.25x minus 4. So again, this one is going to intersect at -4, and it's going to have a gradient of 0.25. So m equals 0.25. Rewriting that as a fraction, it's 1/4. So going down to -4, we'll use a green pen in this instance. And we'll go -4, and then we'll go across 1. Sorry, we'll go up 1, and then we'll go across 4. 1, 2, 3, 4. There we go. Across 4, up 1, bringing the ruler back. And we want our ruler to pass through both points. So the angle is not going to be exact here, but we'll do our best. We'll go, it's pretty close. We'll draw our line. And then I'll annotate it. So this one will be y equals 0.25 x minus 4. Perfect. Now next one, y equals 2x plus 3. So we'll use a purple pen for this one, and looking at this we know the gradient is equal to 2, which is the same as saying 2 over 1, and it's going to cross the y-axis at +3. So let's look for +3 on the axis here, and then knowing rise over run, for every 2 it goes up, it's going to go across 1. So we'll count upwards 2, then across 1, and these are the 2 points it's going to run through. Getting the ruler back up, let's orient it so it passes through both points. 65, 60. That looks sort of okay. Alright, drawing the line. Done. And then I'm going to annotate. So this one is equal to y is equal to 2x plus 3. Cool. Now let's go to a new graph, and we'll graph D, E, and F. So here we go. Looking at D, notice that we're in a different form again. So the constant is the first term, and then the x value is the second term. So looking at this, we know that because the constant is the first one, we can say it's going to intersect at 2. So I'll mark it here, +2. And then we've got an m of -2 over 3. So again, as the rise over the run, we can see that for every 2 we go across or go up, we're going to go across 3. But notice there's a negative. Because there's a negative there, we're going to go down 2 and then across 3. So we'll go down 2 here, across 3, and these will be our 2 points here. lining up the ruler to fit through both points. There we go. Then putting the arrowheads on our line. So the reason we need the arrowheads is to denote that the line goes onwards to positive infinity all the way to negative infinity. So this is y equals 2 minus 2 over 3x. Or you could change it around so it was negative 2 over 3x plus 2. Either way is acceptable. Now e, we have y equals negative 2x minus 6 all over 3. Again, we're not in a form that we can really work with, so we'll change it to slope-intercept form, and we'll say that this becomes negative 2x over 3 plus, and 6 divided by 3 is 2. So you might be asking, why is this a plus and not a negative? The reason being that if we put the brackets in front, this negative here, it's going to go up and turn this 2x into a negative. So up here it's positive because there's a negative here. It's going to change it to the positive. It's going to change positive 2x to negative 2x, and this negative 6 here, this negative will come in and change the negative 6x to a positive, or change the negative 6 to a positive 6, and then dividing through by 3, it will change it to 6 divided by 3 is 2. So looking at that, we've got a gradient of 2 over 3 and an intercept of 2. So I'll mark 2 on the map, positive 2 here, and then the gradient itself is going to be negative 2 over 3, so rise over the run. And notice it's a negative, so for every 2 we go down, we're going to go across 3. So it's actually the same as this blue one. So would you believe this blue line also represents this equation here? So I'll simply draw it over the top. So negative 2x minus 6 and 3. And finally we're on to f, y plus x equals 2x plus 3. Well, notice once again, this isn't in the slope-intercept form because y is not the subject. It's actually an expression on the left-hand side here with an x involved. So what we need to do to get it into slope-intercept form is get rid of this x and make y the subject. So to do that, I'll simply take x from both sides of the equation. So this will become y equals 2x minus x plus 3. Which will simplify down to x plus 3. Looking at that, the gradient is going to be 1 over 1, and the y-intercept will be a positive 3. So marking positive 3 here, well, it's getting a little bit messy. And then we'll go 1 across and 1 up. There we go. And we'll draw a line through those 2 points. And then I'll annotate that line and write y equals x plus 3. So in summary, going back, what we've done is we've graphed these equations, or we've turned these equations into the graphical representation using the slope-intercept form. The slope being m, or the gradient, and the intercept being the point at which it crosses the y-axis. Now, before we're done for this learning intention, there are 2 more special cases that we need to look at. Those being vertical and horizontal lines. my apologies. So just quickly get rid of that graph because it's not appropriate. So we've got two cases, vertical and horizontal lines. So these are two special cases. If you recall in Learning Intention 2, we had a look at where we had a gradient of 0 and a gradient where it was undefined. So the first case we'll look at is where we have a gradient of 0. So notice in the graph on the right, you can see that as the values of x change, the values of y remain unchanged. Now what this looks like on Desmos is, if I hit play, notice that the line itself crosses the y-axis at whatever we specify the constant to be. And we can write it as y equals the constant. So if the line crosses at 3, then we could say y equals 3. Well, I'll hit play and see what's happening. So whatever the constant is, that's where this horizontal line crosses. Now going back, as I mentioned, we can write this situation as y equals c, where c is a numerical value. And c is the point at where we cross the y-axis. So that's the situation of a horizontal line. We write it as y equals whatever number it crosses at. Now the other case is the vertical lines. So the vertical line has an undefined gradient. What does that mean? Well, it means something like m equals 1 divided by 0, which is huge. So how many times does 0 fit into 1? Well, it can fit an infinite amount of times. So this gradient of infinite results in a vertical line. So one way to look at it is, as the values of y, or as the values of y change, the value of x is unchanged. Or you could say y is independent of x, and we model that as x equals n being an arbitrary number. What does that look on Desmos, or look like on Desmos? Let's hit play. And you can see, so I've set n to be between -6 and 6. Whatever value n takes on, that's the point at which this line crosses or intersects the x-axis. So see how it moves along. For a positive n, it's on the right-hand side of the y-axis, and for a negative n, it's on the left-hand side. So you can see that where n, or n, is a point at which the line intersects the x-axis. So if we intersected, in this case we're doing it at n equals -3, this particular model here would be x equals -3. So in conclusion, what we learned today was how to graph a line represented in slope-intercept form, and then we had a look at lines, or vertical and horizontal lines.